In this video, we're going to learn about rate laws and how we determine a rate law and the order of reaction. So the order of reaction is the factor by which the concentration of the reactant affects the rate of reaction. So changing the concentration of a reactant can have varying effects on the rate. So you have to actually deduce this by experimental data. It can't be determined by the coefficients in the chemical equation. You may double a reactant's concentration and have no impact at all on the rate of reaction. Or you may double it and it'll cause the rate of reaction to double as well. So we have to explore these things. So the rate law gives the relationship between the reactant concentrations and the rate of reaction. We don't include the products as part of the rate law. We only take a look at the reactants. So a rate expression is written like this. So rate is equal to K, which is the rate constant, times the concentration of the first reactant to the power of the order of the reaction. We'll talk about that a little bit later. We times that by the concentration of the second reactant, if there is one, time to the power of that order of reaction, and then times the concentration of the third to the power of that order of reaction. In moles, and that comes out to moles per liter over time, or per time, unit of time. Reaction order is equal to all three of those order of reactions. So if this is a factor of 1, this is 0, and this is 1, the total order of reaction would be 2, because 1 plus 0 plus 2. So now we are going to take a little bit further look. So if we look at this example, rate is equal to K times the concentration of A to the power of 1 times the concentration of B to the power of 2. The overall reaction order is 1 plus 2, so that's equal to 3. So the order of this reaction is 3. We can also look at the reaction order of individual reactants. So it's first order with respect to A and it's second order with respect to B. So let's just take a look at the different orders of reaction and see how they would affect and how they would be written as a rate expression. So if the order of reaction is 0, the rate expression would be rate equals K times the concentration to the power of 0. And what this means is that rate isn't being affected by the concentration of A. Any change in A's concentration will not affect the rate of reaction. If an order of reaction is first order, the rate expression would be rate equals K times the concentration to the power of 1. So this means that rate is directly proportional to A. So if the concentration of A is doubled, the rate of reaction would double too. If we half the concentration, we would half the rate of the reaction, and so on. If the order of reaction is second order, the rate would be equal to K times the concentration of A squared. So rate changes as the square of the concentration of A. So if the concentration of A is tripled, the rate of reaction would be increased by a factor of 9 because we would square the 3. So it would be 9. So what is the rate constant? The rate constant K is a constant for a given temperature. So you have to perform all of your experiments at the same temperature to determine the rate constant. If the temperature changes, the rate constant changes too. For fast reactions, you'll have a large K value, and for slow reactions, you'd have a small K value. And that would make sense because you're multiplying a big number, you'd get a big rate. If you're multiplying a smaller number, you would get a smaller rate. So now we'll take a look at finding the order of reaction. So if we look at this example, the following reaction was performed at the same temperature under different concentrations. So the hypochlorite ion reacted with the iodide ion to make iodite and chloride ions. So we are going to use the data on the next slide to determine the rate law for the reaction. So we can see that this balanced equation are all factors of 1. So here's our data table. So we did 5 different experiments. We measured the concentrations and the initial rate of reaction. So the hypochlorite ion, we have 2.0 times 10 to the power of negative 3 moles per liter. The initial concentration of iodide is 4 times 10 to the minus 3, and our initial rate of reaction was this. So we can actually then take a look at a few different reactions. So if we double the hypochlorite concentration but keep the iodide concentration the same, we can take a look and find out what effect it will have on the rate of reaction. And then we can also then keep the hypochlorite concentration the same. So if we compare experiment 1 and 4 and we have the iodide concentration, we can take a look at the impact on the rate of reaction. So we're going to do that. So when we look at the data, we noticed that when we doubled the hypochlorite concentration and kept the iodide concentration constant, the rate doubled. So if the rate doubled when we doubled the concentration of the hypochlorite, it's first order with respect to the hypochlorite. So we figured out that part. Now we need to find the order of reaction for iodide. So we compared reactions 1 and 4, and if you go back and look, if we keep the hypochlorite concentration constant and we have the iodide concentration, we'll see that the rate of reaction also was halved. So the rate halved too. So this means that it's first order with respect to iodide as well. So now let's calculate the rate expression. Rate is equal to K times the concentration of the first reactant to its order of reaction times the concentration of the second reactant time to the power of its order of reaction. So it's equal to K times the concentration of hypochlorite and its first order, so you could write a 1 or just leave that, times the concentration of the second one, iodide. Put our little ion sign charges there. And that's the rate expression. Now we can take that and find out what the value of K is by substituting in data. So now we can plug our values in. So the rate was 2.0 times 10 to the minus 3. And that's equal to K times, and we put in the values, 2.0, the concentration of hypochlorite was 2.0 times 10 to the negative 3, times 4.0 times 10 to the negative 3 for the concentration of iodide. And then we need to isolate K. So we need to divide these two values by the other. So by rearranging, K is going to equal, K is equal to 64 moles per liter second. So we're going to work through another example. This might have happened at a different temperature. So we're going to find the rate expression for the same reaction, but this time our concentration values are a little different. So we have this. We have the initial reaction where we keep everything the same. And then in one example, we're going to double the one reactant, and in the other one, we're going to double the other reactant and see what the factors were that changed. So another way of solving this is to set up a table like this where you have the two columns demonstrating what happens when you perform different changes in the concentration. So when we double the hypochlorite and keep the other the same, the iodide the same, this is what we see. So we double the hypochlorite and the rate multiplies by 2. So then another way of figuring out what the order of reaction is, you write A to the X equals B. So A would be what you did to the concentration. X would be the power or the order of reaction, and then B would be what happens to the rate. So 2 to the X equals 2. X must be 1. So the order of reaction is first order. So this is one way of doing it. The other one, if we double the concentration of iodide, the rate increases by 4. So if we apply the same rule, 2 to the X equals 4. Well, it must be 2 to the power of 2, so it's a second order reaction. So our rate expression would be rate equals K times OCl minus times the concentration of iodide to the power of 2. So this is to the power of 1. So that's our rate expression. So once again, we can sub in our values to solve for K. So in this example, it's going to be the rate was 1.75 times 10 to the power of 4 equals K. And then we sub in our concentration. So 1.7 times 10 to the minus 3, and that was first order, times 1.7 times 10 to the minus 3, and this one was second order. So if we rearrange and isolate for K, K is equal to 3.56 times 10 to the power of 12 liters squared per mole squared second. And that's how you solve for the rate of reaction. If we were to look at graphs of concentration versus time for the different orders of reactions, you would see a trend. So a zero order reaction would be linear, a first order reaction would be exponential, and then a second order reaction would be a quadratic function. If we took a look at and we graphed the rate versus the concentration, a zero order reaction would be horizontal. A first order would be direct proportion, so it would be linear, and then a second order would be parabolic. There would be a parabolic curve. If we were looking at the half-life of something, it's the time it takes for the concentration of reactant to decrease by half, so T half. In first order reactions, the half-life is constant, and this is important in radioactive decay because we can figure out how long something that is radioactive it would take for it to completely break down and be no longer dangerous.